Welcome to frequency synthesis and analysis. All right, let's work through some terminology here. Let's start out. Frequency synthesis, just like an AC signal will superimpose on DC. So when we put those two signals together and we're measuring that in our oscilloscope, we'll see that they're combined. This will also occur when two different frequencies are combined, so that they'll synthesize together. And we can, synthesis is a noun, it's composition or combination of parts or elements so as to form a new whole. That's a Merriam-Webster's definition. Frequency synthesis is the process of combining multiple sine waves to produce a new desired waveform. Okay. Now, a perfect square wave. Perfect square waves are comprised of an infinite number of odd harmonic sine waves. So all of the odd harmonic sine waves put together will create a perfect square wave. Okay, sawtooth, exponential, and triangular waveforms are comprised of a combination of odd and even harmonic sine waves. So what are harmonics? A harmonic is a multiple of the fundamental. Harmonics are numbered according to their ratio to the fundamental, and the number of harmonics are infinite. The number is infinite. However, the amplitude of each harmonic will successfully decrease, so it keeps dividing. The amplitude goes down as the frequency increases. Okay, so this is kind of a table showing what's going on with the frequencies and with the amplitude of that harmonic. So the fundamental is your base frequency, and it's at a frequency and at a voltage. So the second harmonic is 2 times whatever that fundamental frequency is, and you can see that the voltage of the second harmonic is basically divided by 2. And this goes on and on and on. So the third harmonic is 3 times the base frequency, the fundamental frequency, and the amplitudes can be divided by 3. This goes all the way to infinite. But you can imagine the 100th harmonic is the fundamental times 100, and that amplitude is going to be relatively small. Okay, so we mentioned in the previous slide that perfect square waves are comprised of all the odd harmonics. So in this example, example 1, you can see we've got our fundamental frequency here, and we've also got the third harmonic. So VA is the fundamental, VB is the third harmonic, and simply adding those two waveforms together, we get something that's starting to look like a square wave. All right, here's the second example, and you can see we've got the fundamental again. We've got the third harmonic, and you can see that it's about the third of the amplitude of the original, and 3 times the frequency. And we've also got the fifth harmonic, so we're adding the next odd harmonic, and you can see that the output waveform, when the fundamental, the third, and the fifth harmonics are added together, you can see it's looking even more like a square wave. Okay, so harmonic analysis is kind of the opposite of frequency synthesis. So we're trying to figure out a few different things, and basically bandwidth is equal to the number of harmonics times the fundamental, and we can manipulate that formula so that we get the number of harmonics will be equal to the bandwidth divided by the fundamental, and the fundamental is also equal to the bandwidth divided by the number of harmonics. Okay, so if we want to calculate the number of harmonics that will pass through an amplifier with a known cutoff frequency, we would divide the bandwidth by the fundamental of the square wave. So for example, suppose we have a square wave with a fundamental frequency of 1 kHz, and that's applied to an amplifier that has an upper cutoff frequency of 15 kHz. We know that if we divide the bandwidth by the fundamental, that we should get 15 harmonics out. Now, if we do the same thing and we change the fundamental to 5 kHz, so we've changed the frequency of the square wave to 5 kHz, we put it in the same amplifier, we would expect to only get 3 harmonics out. The first, the second, and the third. So the number of harmonics, so we've got the bandwidth of 15K now divided by the new fundamental of 5 kHz, we get the 3 harmonics. The third harmonic is the only one that will pass through the amplifier. So the first, the second, and the third harmonic. So Fourier analysis is the mathematical function by which waveforms can be analyzed to determine their harmonic content. So it's kind of working backwards. We've got a waveform and we're working backwards and trying to figure out what the harmonic content is. What are the waveforms that make up this waveform? That's Fourier analysis. And then you can go to this website and check out some examples of Fourier analysis.